Bonjour and welcome to everyone assembled either in the Ford Robotics building or on Zoom with us today. I am Professor Jesse Grizzle. I'm joining you from the southern coast of France while I am on sabbatical. I am Wami's very proud advisor. I want to give a thanks to the committee for all the support they've given to Wami. Ram, I want to give you a special thanks for the great environment in the Ron and Regina Walk Lab. You also provided a year of financial support for Wami, and you've been advocating for her post-graduation career. But Chad, I'm saving my extra special deepest thanks for you for understanding that Wami and I would make a great team. Without your intervention, we would not be here today. So this is all to your credit, and Wami's, of course. So with that, let me introduce the star of this morning's event. Wami came to the Biped Lab in fall 2020, right in the middle of the pandemic with no vaccines on site. Not deterred, she hit the ground running and is on track to complete her PhD in 3.5 years. Wami, if successful today, you'll be the first Black woman to earn a PhD in robotics at the University of Michigan. No pressure. And with that, Wami, I give you the stage.
Excellent. Well, thank you so much for those kind words, Jesse. And thank you everyone for attending my PhD defense today. I'm excited to talk to you all and share my research. So this thesis is entitled Ascending New Heights in Enhancing Bipedal Robotic Locomotion Through Stair Climbing. I want to help create a robot-assisted world where robots of all types are helping humans from all walks of life. So think robot butlers and robot firefighters, robots doing those boring and dangerous tasks while we humans get to do the fun and safe tasks. However, we live in a world built by and for bipedal beings. And thus, for our robots to be useful in a robot-centric world or a robot-assisted world, they need to be able to navigate through common human terrain, such as stairs. So that leads to the objective of this work, which is to create a novel stair climbing algorithm to allow for smooth navigation upstairs. That begs the question though, can't bipedal robots already walk upstairs? Well, if we look into literature, certainly we see that strides have been made. For example, you've probably seen fully actuated robots, for example, Boston Dynamics Atlas robot, where it's able to move quite agilely, especially even going upstairs. However, I want to explore the underactuated robots. Underactuated robots have the benefit of being lighter and typically can be more agile than fully actuated robots. We've also seen this work right here where the authors are able to get this underactuated robot to navigate through gentle slopes by approximating it as piecewise linear terrain. And in theory, one could extend this work to stair climbing applications. So by basically approximating stair geometry as also piecewise linear terrain. However, I want to take an approach that's a little bit more friendlier to sudden changes in center of mass height. And then there's also been this work right here where the authors remarkably has also been able to get an underactuated robot to navigate up and down stairs using reinforcement learning. However, the stairs are basically seen as unseen perturbations, which means in order for this robot to get up and down the stairs, it's having to exert quite a lot of torque to maintain its balance. And you can imagine in like settings such as like hospitals, for example, you don't want to see a robot that's like stomping up and down the stairs. That is not a comforting sight to see. So I want to take an approach to stair climbing that's a little bit more delicate, if you will. There's also been most recently this work right here where the authors were able to get an underactuated robot to walk on constrained footholds, including on stairs. This is just an approach to the stair climbing problem. I take a different approach, as you'll see shortly. So the contributions of this work, I'm going to get a little bit jargony here, but I will be explaining these terms later on. But just to like lay it all out, the contributions of this work is that I have this exploitation of a variation of what's called the ALIP model, the Angular Momentum Linear Inverted Pendulum model. that allows for the center of mass height to vary within a step. I also have this novel combination of virtual constraint-based control, using model predictive control to stabilize the stair climbing gait, and also incorporating this often neglected stance toe motor. I have full validation in the sim mechanics simulation environment and partial validation on hardware. So the rest of the presentation is outlined as follows. We already went through the motivation and background. I'll next be talking about the system dynamics of the robot that will be featured in this thesis, as well as the control design. So specifically talking about the nominal trajectories, the new robot model developed in this thesis, the virtual constraint-based control method, as well as this intelligent ankle torque computation plus lateral foot placement stabilization method. We'll then get into some awesome results. So looking at first the mechanics simulation environment, as well as the hardware results, and then finally end in future work. So let's meet the robot of the hour, the Cassie bipedal robot. Cassie is a underactuated bipedal robot built by the company Agility Robotics. It has 10 actuators total, 5 on each leg. Each leg is also 7 degrees of freedom, where 2 of the degrees of freedom are passive. To the left, you'll see the generalized coordinate vector of the Cassie robot, where the first 6 coordinates correspond to the floating base coordinates, and these joints correspond to its passive joints. We represent systems like Cassie, bipedal systems, as hybrid systems. What do I mean by that? So first, there's this continuous domain where, let's say, the swing foot, the right foot, is now in the air, and right before it touches the ground, that ends the continuous domain. And when it touches the ground or impacts the ground, that's when we enter the discrete domain. And then since we have 2 feet, we do the same thing on the other side. So now the left leg's in the air, it's in that continuous domain. When it touches the ground, now we're in that discrete domain. And of course, we repeat this because bipedal robots, we walk multiple steps. We're going to look at the equations that govern both of these domains, starting with the continuous domain. So I use the floating base Euler-Lagrange approach. So these are the equations of motion that the engineers and robotists in the room probably are very familiar with. The matrices, as well as all the vectors, are defined as follows. Pretty standard for our robot equations. However, I don't want you to be fooled by, quote unquote, how simple this equation looks. Indeed, for a robot as complicated as Cassie, it's quite a lot to deal with. So just to, I guess, illustrate, let's just look at the mass inertia matrix. That is this first matrix right here. And let's look at it for just the 3-link walker. This is a very simple biped robot. And so if I were to write it all out symbolically in Times New Roman 10-point font in Microsoft Word, it looks like this, which is actually not that bad. You could probably derive this by hand and not be too traumatized. Then we have the 5-link walker. So getting a little bit more complicated. The 5-link walker is still a planar robot like the 3-link walker, but now has 7 degrees of freedom. If you were to write this one out in Times New Roman 10-point font, it would look like this. I wouldn't want to derive that by hand. I would not derive that by hand. So you can imagine, what does Cassie's mass inertia matrix? Cassie doesn't think it's that bad. I say it is that bad. Yeah, so it's thousands of pages. It's a lot. Cassie is a lot to deal with. And that's why we love Cassie. So all that to say, though, these equations are quite complicated. So now let's move on to the discrete domain. We talked about the continuous dynamics. Let's look at the discrete domain dynamics. We start with the robot equations, similar to what we saw before in the continuous domain, but now you'll notice these new terms corresponding to the swing foot. So in that discrete domain, that's when that swing foot impacts the ground. So now we have to account for those forces that impact the ground, which is what we have here. I'm going to integrate this equation from the time right before impact, time t minus, to the time right after impact, which is t plus, and we get this, where the q dot values, or q dot minus, is the generalized velocities right before impact, and q dot plus are the generalized velocities right after impact. I'm going to impose this non-slipping condition. So what do I mean by this? This means that, like, once that right foot impacts the ground or the swing foot impacts the ground, we're not going to slip away. That's a completely different problem outside the scope of this work. So we impose this non-slip condition. Taking these two equations right here, I'm going to smush them all together and into this matrix form, do a little rearranging, and we have what is called our impact map. This describes the discrete domain dynamics. And again, do not be fooled by how simple this equation looks. For Cassie, it is quite a nightmare to work with. So that's our robot. How do we get this complicated robot to walk upstairs? So now I'm going to talk to you about my control design philosophy. Cassie has 20 degrees of freedom. How are we going to regulate all of them? Well, 9 of them are actually already taken care of due to the holonomial constraints in the continuous domain. Specifically, there are 4 from Cassie's springs and 5 from Cassie's stance foot. I'm then going to choose to control 9 of Cassie's actuators via passivity-based control, and this will control another 9 degrees of freedom. And then for that last actuator, the 10th actuator, which is the stance toe actuator, I'm going to use that to control the sagittal plane center of mass dynamics. And this right here represents one of the novel contributions of this work, because previous methods would use a foot placement to control this plane, and I don't do this. And the reason is, just think about stair geometry. You have very limited, I guess, geometry to work with in that sagittal plane. So using a foot placement strategy is not a very reliable strategy, hence why I instead use the stance toe actuator. And then finally, for that last degree of freedom, I will use a lateral foot placement controller to control the frontal plane center of mass dynamics. And you might be like, hey, Wami, you just said you can't use foot placement in the sagittal plane, so why are you using it in the frontal plane? Well, again, just think about the geometry of stairs. Stairs are pretty wide, so using a foot placement strategy in that plane of motion is a completely valid approach, so that's what we do. So that's my control design philosophy. Let's look at my overall controller structure. So first, I'm going to generate Cassie's nominal trajectories. I'm then going to develop this new and improved robot model, and then use this virtual constraint-based control using passivity-based control, which I kind of hinted at in that previous slide. I want to point out that those nominal trajectories from the first step, I use them here in the virtual constraint-based control. I also use the new and improved robot model in this particular step right here. And then the 4th step right here, we use the intelligent ankle torque computation plus lateral foot placement. And again, I use the nominal trajectories from before in this step right here, as well as that new and improved robot model is also incorporated in this step right here, which we'll see. And all this together will result into stair climbing. So let's look at each of these components one by one, starting with the nominal trajectories. I use what's called the Fast Robot Optimization and Simulation Toolkit, or FROST. So to the right of your screen, you're going to look at you see the full order model of Cassie in the FROST environment. I impose boundary conditions to ensure that there's periodicity that's achieved and to include stair geometry. So you'll notice that this animation here is kind of like doing this arch motion with the feet. That is those boundary conditions at play. So that means that once we apply this onto the actual model of Cassie, that it will avoid those stair geometries. These trajectories were generated to specifically be used in the virtual constraint-based control method that I mentioned before, as well as that intelligent ankle torque computation or model predictive control in that fourth step. I generate trajectories not for just stairs, but also for flat ground and various inclines. And the reason for this is because I don't want my controller just to be able to climb upstairs. It should also be able to climb up, or it should be able to navigate through various different gates. So it's able to climb upstairs, it's able to do flat ground walking, it can do inclines, and it can do those transitions between like flat ground to various inclines. Now let's look at this new and improved robot model. First, starting with what was the old model. We have what's called the linear inverted pendulum model, which basically means it's a simplified representation of the dynamics of an inverted pendulum. We bipedal roboticists would apply the LIP model onto bipedal robotic systems by basically approximating that robot as a point mass on massless legs. So what I mean by this, if you look at the picture of Cassie on the bottom left-hand corner of your screen, that's the full order model of Cassie. We would represent this as a LIP model by basically like this. So it's centrous of mass, and then that there's this vector going from that center of mass, or from the contact point to the center of mass. And so that would be the LIP model representation of this bipedal robot. Applications of this robot or of this LIP model will typically assume that there's constant center of mass height, And it would use center of mass velocity to quantify balance. However, these assumptions are not good for a stair climbing controller. So let's take it one step further. Upgrade from the lip model to what's called the Angular Momentum Linear Inverted Pendulum model, or the ALIP model. As the name kind of implies, the ALIP model is just a derivation from the lip model, but instead of using center of mass velocity, we now use angular momentum as the key variable. And the question might be, well, why use this different variable? Why not use center of mass velocity? Well, let's look at how center of mass velocity evolves over time for the lip model. So here I have a graph of how center of mass velocity evolves over time for the lip model. Let's compare this with a full order model of Cassie. This is what its center of mass velocity looks like over time. And as you can see, these two graphs are pretty different. That's not good. The reason why we use simplified models like the lip model is such that it will act as like a good representation of the full order model that we're trying to represent. So the fact that these two graphs are not similar is not good. So now let's compare this to the angular momentum about the contact point. The lip model graph, it looks like this. And now for the full order model of Cassie, it looks like this. And as you can see, these two graphs are very similar. That's great. That means that the angular momentum is a more faithful variable to the to represent Cassie in the, I guess, ALIP model format. I take it one step further in this thesis. So previous implementations of the ALIP model would define the center of mass states like so, where this XC variable is the center of mass horizontal displacement, and Ly is the angular momentum about the contact point, and then the full order center of mass dynamics are defined like this. We know from previous works that the Ly-LC term right here is actually negligible for Cassie-like robots, so that term goes away. And this is where it gets interesting for the previous model of the ALIP. People would assume constant center of mass velocity, which means that this Z dot term would go away. Now, for the new variation of the ALIP model that I use in this work, I reparameterize the lip model yet again. I add these two new variables, theta C and RC, which correspond to center mass, angle, as well as pendulum length. So now I define my center mass states like this, where theta C is now one of the variables as opposed to XC. And thus the full order center mass dynamics are defined like this, where we know for Cassie-like robots, this LYC term is still negligible. So that's already been proven. But now, instead of that constant center of mass height assumption, I make a small angle approximation. So I say that theta C is sufficiently small that sine theta C is approximately equal to theta C. And just to really drive home this point, the RC variable, which is pendulum length, which kind of is like a proxy to the center mass height, that variable is time varying. But now you might be wondering, well, you're still making an assumption. You're saying that theta C is a small angle. How can you say that? I will show you how. If you look at the nominal trajectories for theta C as it evolves over time for stair climbing, so stair climbing is a pretty rigorous gait. Theta C evolves from about -0.2 radians to about 0.1 radians, which is pretty small. That means that small angular approximation is completely valid. So just to drive home the point, previous ALIP model, you typically assume to have constant center mass height, and usually you would actually use foot placement in this controller strategy. And as I've illustrated before, these are not good assumptions for a stair climbing controller. Versus the new variation ALIP model, it does facilitate for varying pendulum length, and it uses a small angular approximation as opposed to constant center of mass height assumption. And thus, it can be used as a much friendlier basis for a stair climbing controller. So now, let's talk about virtual constraint-based control using passivity-based controller. The passivity-based controller is used to determine the values for 9 of Cassie's 10 actuators. I use an output function that's defined as follows, where H, or the virtual constraint, are defined like this. And I want to draw attention to this pendulum length variable. So here you can already see that new model at play. We use it here. And those nominal trajectories from before are also being used to determine the desired trajectories for the virtual constraints. I'm designing a controller such that this control law holds. So where KP and KD are user-defined parameters, and D bar and C bar are derived from Cassie's robot equations. And I have the full derivation in my written thesis. I'm not going to derive it here unless you want me to later on. So those are those variables. And I like to use the passivity-based controller as opposed to, like, let's say, input-output linearization, because passivity-based control retains the natural dynamics of the system, versus input-output, it would cross out those dynamics, which is not good. You want to make sure your controller is able to, I guess, account for the natural dynamics of the system. So now let's get into the intelligent ankle torque computation plus lateral foot placement strategy. I use what's called model predictive control to determine Cassie's ankle torques. So the premise of model predictive control is to use a model of the system to predict how that system will evolve over an interval of time, and then use that to determine an optimal set of control inputs to achieve a desired goal. So how do we implement this? Well, the model of the system is going to be that new model that I introduced earlier on. And the prediction step, I'm going to actually say that the trajectories I want to follow are the nominal trajectories from the first step. So now, how do I get this model to follow these trajectories? What control strategy did I use? I use a quadratic program. So the roboticists and engineers in the room will recognize this as a standard QP. So now, let's get into the lateral foot placement strategy. I use this to determine, I determine the lateral foot placement by using this new variation of the ellipse model. So I'm showing you the dynamics to the states, similar to what you saw before, except for everything's now defined with respect to the frontal plane as opposed to the sagittal plane. So for example, you see an Ly or Lx variable instead of an Ly. The way that you determine foot placement with this new variation of the ellipse model is similar to the old, except for the old model does allow for a closed form solution. However, this model, you have to do some interpolation, which I go into more detail about in the written thesis. So now we have our controller. All this should yield to stair climbing. So let's see how this controller performs in actuality. So insights from its sim mechanics simulation results. First, a little overview of the sim mechanics environment. We use compliant ground. It also factors for Cassie's realistic springs, and we're implementing the full controller in here, so there's no abbreviation happening here. We also integrate or use state estimation just as we would do on hardware. So that means that Cassie has an IMU and encoders. We use a Kalman filter to estimate its states for the controller. We also do real-time computations in this sim mechanics simulation environment. For Cassie, that means that the execution time has to be 2 kilohertz, which all the roboticists in the room knows that is a really fast execution time. It's quite a nightmare to work with. So all that to say that this is a very rigorous simulation environment, and thus controllers we found in our lab, controllers that work in sim mechanics typically also work on the hardware. So first, let's just see if my controller can walk on flat ground. I mentioned that I want my controller to do more than just stair climbing. Can it walk on flat ground? The way to define this experiment is first I tell Cassie to stand for 2 seconds, then march in place for 4 seconds, then walk forward for 8 seconds, and then do fixed step walking for 6 seconds. The last step, the fixed step walking, is the key part in this experiment. So if you imagine like stair climbing, you're kind of walking with fixed steps to get up those stairs. Here, I basically like translate that notion in like onto flat ground. So now you're walking fixed steps on flat ground. And we see how this performs. So right now you're looking at the graphs of angular momentum and center mass angle as it evolves over time for the experiment. When you engage the ankle torque, that intelligent ankle torque, Cassie's able to complete that experiment just fine. But when you turn off ankle torque, during that fixed step walking point, Cassie falls, as is illustrated by the sudden jump in values and then the subsequent loss of data that indicates Cassie falls. How robust is my controller? Can it withstand perturbations? So I perturb the system by reducing all of Cassie's motors by 1/5 of their control values for 50 milliseconds to see if Cassie's able to recover from that. I do it first during the march in place section of the experiment. And with ankle torque, again, we can see that Cassie is able to recover, and you can see how much this perturbation affects the system. Like by looking at the angular momentum values, it shifts by about 5 units downward, so that's quite a large perturbation. But without ankle torque, Cassie's not able to recover from this perturbation. I do the same thing during the fixed step walking phase, and again, Cassie's able to recover when ankle torque is engaged, but without ankle torque, no surprise here, it still falls. It wasn't able to do the fixed step walking without the perturbation, so it's no surprise that it's not able to fixed step with perturbations. But can it climb upstairs? Well, certainly I would hope so, otherwise I would not be standing here today. So yes, the controller does work upstairs. Cassie's able to get all the way up to the top of, I believe, 10 or 11 steps here with ankle torque engaged. Without the ankle torque, Cassie falls after just a few steps. And something I want to show you here is just looking at the values of the ankle torque. The magnitude is quite small, and yet these small values are the difference between whether Cassie is able to get to the top of a staircase versus Cassie falling flat on its back. Hardware. Can this controller work in real life? Let's see. Well, so first in this experiment, I have Cassie on a moving treadmill. So this treadmill is going at 0.9 meters per second, and it's slowly inclining from 0 degrees all the way up to the maximum incline of 20 degrees, and then back down to 0 degrees. I'm employing just 3 nominal trajectories, specifically nominal trajectories for 0 degree incline, 8 degree incline, as well as 15 degree incline. And Cassie's able to complete this entire experiment just fine. The awesome thing here is that this tells us that we don't need to have a nominal trajectory for every single circumstance that we have. So for example, the 0 degree incline is or 0 degree incline trajectory is able to accommodate inclines from 0 to 7 degrees. So that shows the robustness of this controller. Additionally, all the nominal trajectories are anticipating or expecting a speed of 0.5 meters per second. And yet I'm having, in the experiment, having Cassie move at 0.9 meters per second. So again, that shows the robustness of this controller. I'm not gonna play this entire video because it's 5 minutes long, but it's referenced in the thesis, so you can watch the full video with the sound and all of that on your own time. So now let's look at this other experiment. Here, I'm having Cassie start on a stationary flat ground and then walk onto a moving treadmill. I want you to picture yourself trying to walk on a moving treadmill. That's difficult for us humans to do. So that's, again, showing the robustness of this controller. And when Cassie gets on this moving treadmill, I then further increase the speed up to 2.2 meters per second. Previous controllers that also work on Cassie was able to get walking speeds of about 2.1 meters per second. So this shows us that my controller works just as well, if not a little bit better, on flat ground as previous controllers. And again, I have the volume muted here, but if you hear this experiment in person, it's quite loud and scary, especially when that treadmill is like really inclined. So again, I would reference the thesis if you want to watch the videos with the sound on. In this experiment, I do something similar, but except for now I'm having Cassie start from stationary flat ground and then walk onto an inclined moving treadmill where the treadmill is inclined at 20 degrees. And again, picture yourself trying to start from walk from a flat ground to an inclined moving treadmill yourself. That's difficult for us to do. So now I'm having Cassie do the same thing. And again, it's quite, I guess, intimidating when you see this work in real life, because the treadmill is like really loud. My desk is right beyond this treadmill right here, and it's above my desk. So it's very, very cool to see this controller at work. Another feature that you see in human life is moving walkways. You might see this in like airports or fancy malls and other such similar settings. So I want to see if Cassie could also navigate through moving walkways. So we do that. So now we just have Cassie walk on from the other side of the treadmill. And in real life, you'll see moving walkways move from about like 0.5 meters per second to about 0.83 meters per second. So we have Cassie do that. Something I want to illustrate here is that the gantry in here is which is the thing that would catch Cassie if it would fall, is acting as a large disturbance here, because that gantry is not designed to move as far back as we needed Cassie to start. So while Cassie's like doing this, trying to get set up and start on the other side, the gantry is kind of like constantly tugging at Cassie. And yet, despite this huge disturbance, the controller is still able to get Cassie from the from one side of the moving walkway all the way up to the other side of the moving walkway. We repeat this experiment for a faster moving walkway. So this is like about the upper end of what you'll see in real life. And again, Cassie's able to complete this experiment just fine. And here, I actually make a little mistake when I have Cassie walk across this moving walkway. The approach angle here is at a little awkward diagonal. And yet, despite this awkward diagonal approach and this gantry that's tugging at it, Cassie's able to complete this experiment. I repeat the experiment yet again, but now I have the treadmill move at 1.2 meters per second. And you probably won't see a moving walkway move this fast in real life. And here, I really want to show you, Cassie's actually about to stumble here in a couple of seconds. Wait for it, it's finding its footing and stumbles. And yet, Cassie's able to recover and complete this experiment. So this is just showing you how much that moving walkway or the gantry is affecting the system. All that tugging was causing Cassie to stumble, and yet the controller was able to not only recover, but still have Cassie walk across the moving walkway. Additionally, I make the same mistake here where Cassie, when it finally gets on that moving walkway, it's approaching at an even more awkward diagonal approach angle, and yet Cassie is still able to get across just fine. So that's exciting. So I'll let this go one more time because it's really fun to see. So Cassie recovers, and now it's about to, I guess, cross the moving walkway. It's having this awkward diagonal approach angle. You can see it's kind of like stumbling, and yet it's still able to get across and complete the experiment. And a really cool thing is that this video was actually recently featured in the IEEE Spectrum Video Friday last year on November 24th. So that was very exciting to see. All right, so summary of what we just saw. We saw that we developed a novel stair climbing controller by generating nominal trajectories in Frost, using this new variation of the ALIP model, as well as incorporating a vertical constraint-based control using passivity-based control. We also incorporated this intelligent ankle torque computation using model predictive control and applied this controller both on a full order model of Cassie and mechanics simulation environment and on hardware. Publications of this work include the following. I have another paper on the way, so excited about that. Future work would next be first stair climbing on hardware. So you might be wondering, well, why didn't you get this to work on hardware? Why didn't you get this to work on hardware? Well, something I didn't mention is that Cassie is a very old robot built in 2016, 2017, and it's no longer being supported by the company, which means if and when I break Cassie, that is it. No more hardware experiment. You can't get an next Cassie. So I've been really deliberate in making sure that I take very slow steps on these experiments. But the stair climbing on hardware is the next step. I also want to explore downstairs walking. So it's cool to get upstairs, but once you're up there, what do you do? I want to go downstairs. So I want to extend this controller to downstairs walking. And I want to integrate sensory feedback. So in our lab, we have this awesome perception system built specifically for Cassie. I want to just smack that on Cassie and have Cassie walk autonomously upstairs. And you might be wondering what I'm hoping to do after graduation. Well, I want to stay in academia. In fact, I am currently on the job market doing interviews and applying for positions. So if anyone's in the audience looking for an awesome faculty member, I am here. Cool. All right, and now we are at the part where you guys stare at me while I attempt not to cry, so awesome. And I didn't trust myself to be able to speak off the cuff, so I'm going to forgive me if I read from a script, so just bear with me here. All right, so first, I of course want to thank my committee members. First, to my advisor, Jesse Grizzle. There are not enough words in the English lexicon to express my profound gratitude towards you. Some of you may not know this, but I almost was not able to complete a PhD. I started out in a different PhD program and failed to meet the requirements to complete that program. And I couldn't find a job at the time because it was 2020, and a global pandemic effectively shattered all of my options. But Jesse, upon hearing about my situation, moved heaven and earth to get me into the robotics PhD program. And not only that, but he was getting ready to retire at the time and had no intention of taking any additional students. But he let me into this lab, risking his well-earned retirement just for me. It really takes someone who truly cares and is dedicated to the cause to show such commitment to help a student in need. So thank you, Jesse, for everything. To Chad Jenkins, my mentor, and again, I curse the English lexicon for not having enough words to express how grateful I am to you. Jesse let me into his lab, but Chad was the one who got the ball rolling to get me into robotics. I remember the day that I told Chad that I would be leaving Michigan because I had failed my previous PhD program nearly 4 years ago to this day. But Chad acted immediately, no hesitation. He reached out to his networks and got Jesse on board. And 4 years later, after the day that I told him I am no longer getting a PhD, I am now defending my robotics PhD dissertation in front of him as one of my esteemed committee members. This is my proudest achievement to date, and I have you to thank for helping me get to this second chance. So thank you, Chad. To Ram, your contributions have also played a significant role in why I get to stand before everyone today. From funding part of my degree to offer me professional development advice to even letting me use your Cassie maze when our Cassie Blue refused to work. Many of the cool hardware experiments that I got to show off today would not have been possible if it weren't for a Cassie maze. So thank you for your key contributions that allow me to be here. And to Kier Barton, your invaluable feedback on job applications and support during my qualifying exams were crucial. I remember how terrified I was for my qualification exams. I was worried that I would fail and essentially mess up yet another shot at getting a PhD. But you were very calm and encouraging, and even when I fumbled with my responses, you knew the questions to ask me that would best showcase my knowledge of the material, which put my nerves at ease. So thank you. To all the PhD students in the Bipedal Robotics Lab, I started off my robotics PhD in fall 2020, which was the first semester that was all virtual due to the pandemic. You welcomed me with open arms over Zoom and masked 6 feet apart. Your hospitality helped me find my feet again, and shout out to the especially Dr. Yukai Gong for teaching me everything I know about Rabbit and Cassie. Thank you to all the master students in the Biped Lab, and in particular Ayushi, whose exceptional contributions played a pivotal role in shaping much of this thesis. It has truly been an honor working alongside all of you. To all my Biped Bootcamp mentees, a lot of them are in the audience today, it has been a privilege working alongside you. The Biped Bootcamp is a 100-page technical document that I wrote based off of the mentorship that I received from my advisor, Jesse. It teaches the students the fundamentals of how to model and simulate a 3-link and 5-link biped robot. These are all my students that learned directly under me, and one of them, Ankita, went on to teach students of her own, so I even have grand mentees, which is awesome. I don't think this is all of them. I think there's actually more of them. Yeah. Thank you to all the Michigan Robotics faculty and staff, to Professor Bobby Gregg, who served as my second examiner for my qualification exams. And he also taught me Rob 501 and Rob 510, which is important because he actively enabled me to generate many glorious memes, including the ones that you see here. To Alyssa and Professor Peter Gaskell for supporting the Cassie robot. Whenever I broke Cassie, Alyssa was right there to unbreak Cassie for me and single-handedly saved my degree. Peter similarly also saved my degree by creating a brand new way to power Cassie when we ran into battery problems. You can see a video of that to the right. To Samantha, Jamie, Denise, Kimberly, and so many more people, I owe you all a great deal of gratitude for your support and helping me get through this degree. To my friends and colleagues in Michigan, in Illinois, Alabama, and literally around the world, your companionship through deadlines, exams, concerts, book clubs, travel, and identity crises, as well as so many other precious shared experiences, will forever hold a special place in my heart. Your collective support has been a beacon of strength throughout my academic journey, and I quite literally would not be here without you. So, love you guys. Thank you to my family, to my siblings. Your consistent praise not only made me proud of what I do as an engineer and roboticist, but also provided unwavering strength. To my parents, my first and loudest cheerleaders. Your unconditional love guided me through many challenges. To my mom, who is in the audience today, who is my unofficial, official international traveling companion. We've been around the world together. No plane ride is too far to separate me from her. In fact, she is supposed to be in the middle of a 1-week hospital assignment away from home right now. But when she found out that I was defending today, she immediately booked a flight to Michigan, even if it meant missing 2 days out of her 5-day assignment. My mom is the most caring individual that you will ever meet, as is evident by the way that she shows up. Love you, Mom. And my dad, who also travels the world with me and would have been here today if his flight literally didn't leave back to Nigeria just a few days ago. My dad is the kindest man that you'll ever meet, and you can see it by the way that his staff and colleagues admire and respect him. I also want to acknowledge my extended family, many of whom are on Zoom, and thank you for all your love and support. Finally, last slide, I promise. I wanted to say who this thesis was dedicated to. I wrote the dedication in my written thesis, but since no one's actually going to read that, I am going to say it out loud here while I have your attention. This thesis is dedicated to all the little Black girls who were told that they could not climb. Let them witness your ascension. And yes, that is a picture of miniature me. Look at how far we have climbed. About to complete a PhD program in 3.5 years and be the first Black woman to get a PhD in robotics at the University of Michigan. I am so grateful to all the people I mentioned and to many, many more people who supported me to get to where I'm at today. It really does take a village to raise a child, and as I gaze upon the village that raised me, seated and standing before me, and to those who are on Zoom, tuning in from literally around the world, I'm grateful and blessed to have all of you in my life. So thank you for supporting me. I will pay your kindness forward to the next generations after me. And on that note, I'd like to thank everyone for their kind attention. This ends my presentation, and I can take your questions now.